Hi, I'm Judy Cole, the Executive Vice President and CEO of the MIT Alumni Association, and I'm delighted to welcome you to this web production of the MIT Alumni Association.
I'll be your moderator today, and if it looks like I'm coming to you from a hotel room, that's because I am. I just got out of a conference, a really fascinating conference on science communication here in Durham, North Carolina, so I'm reporting to you from the Sheraton Imperial Conference Center in Durham. So let's do a little bit of housekeeping. So I will be moderating the panel, and I will be relaying questions from you, the audience, to our panelists today. If you want to ask a question, just fill in the form below this screen, and the question will be fed through to me. And then I'll find time during our discussion to put those questions directly to our guests. We'll get to as many of the questions as we can. And if you're good at multitasking, you can also tweet during the session using the hashtag #MITAlum, MITALUM. So today we're patching into 3 MIT alumni in faculty roles at prominent colleges and universities to ask them questions about the Internet of Things. So your phone may be connected to the cloud, but what about your smoke detector? What about your thermostat? What about your curtains? What about your sneakers, your alarm clock, your car, or even your heartbeat? How connected is too connected? Those are some of the interesting questions that the media are kind of grappling with right now, and they also show up as themes in the research of our 3 panelists, whom I'd now like to introduce. So first, I'd like to tell you that joining us from Concordia University in Montreal is Joanna Berzowska, who is an MS from the MIT Media Lab. Next, you're going to meet David Harris, who is a professor of engineering design at Harvey Mudd College. He has an SB and a Master of Engineering from MIT, both from 1994. And our third guest today is Wendi Heinzelman, who is a professor of electrical and computer engineering and dean of graduate studies for arts, sciences, and engineering at the University of Rochester. And she has an MS and a PhD from MIT. The MS was in 1997, and the PhD was in 2000, both in electrical engineering and computer science. So thank you all 3 for joining us today, and we look forward to having a fun discussion today, fun interactive and a very topical discussion about your research, and I think the through line being the Internet of Things today. So let's have each of you tell us a little bit about your research, and I'd like to stay in alphabetical order and go to Joanna first. Could you fill us in about what you're working on these days, and what you did at the Media Lab, and what threads, maybe literal threads, lead back to what you're up to today?
Sure, thanks, Wade. It's a pleasure to be here. So when I was at the Media Lab, this was almost 20 years, actually exactly 20 years ago. It passes really fast. Seems like yesterday. I started out being involved with developing physical interactions. So I came to the Media Lab to develop new kind of experimental graphical user interfaces. But 20 years ago was the beginning of the tangible media sort of movement, I suppose. So I worked with Hiroshi Ishii, who's still at the Media Lab, and we published a lot of papers around tangible interactions at conferences like CHI, Computer-Human Interaction, etc. What I became really interested in is what happens beyond the wrist. So in fact, I even talk about as beyond the wrist interaction. So instead of just tangible kinds of interfaces that we manipulate with our fingers, with our hands, and that we consume, I suppose, with our senses of sight and hearing, etc., I was really interested in what happens on the rest of the body. So I started working with the wearables group at the Media Lab. People like Tad Starner, who now worked for the Google, what is that thing called? Google Glass.
Google Glass, yes.
Etc. But I really was interested in the full body, so I started working on research in electronic textiles, and I'll just show you a couple of minutes. So let me screen share. Et voila. So I run a research lab at Concordia University, which is called XS Labs, and I'm a professor in the Faculty of Fine Arts, in fact. So it's a Department of Design and Computation. So our students both learn color theory and working with wood and metal, but they also learn to program and build their own circuits. So it's all part of one curriculum, but very much with a focus on design, on social cultural aspects. So my research lab at Concordia, XS Labs, deals with both very technical aspects of how do we integrate materials with different electromechanical properties into textiles to build sensors and actuators directly in the textile substrates, but then also, you know, looking at how can we really define function, right? Or how can we define the value that these sorts of electronic garments or smart garments would bring to people? So we're not only looking at health and other very functional kinds of definitions of value, but also looking at how do we redefine our identities, social networks, how can we communicate better with smart garments? And I'm really interested in garments that work with your body, that perhaps make you feel better, give you a different sense of self, and just help improve your quality of life in general. So we both develop a lot of the underlying science and new materials. I collaborate with different chemists and other material scientists to actually develop new kinds of fibers. But then we also create these experiences and these garments that question what does it mean to be connected, and some of them are very provocative. At the same time, I'm also working with a company that's, it's not even called a startup anymore. It was a startup 3.5 years ago, but it's called Signal out of Montreal, where we've developed biometric garments that, I don't know, you might have seen the big announcement by Ralph Lauren at last year's US Open in New York. So Ralph Lauren is actually launching our first line under their brand. So basically biometric garments that focus at this point very much on sports, performance, fitness. And what I found really interesting in this from a research point of view is how can we make these kinds of garments manufacturable at scale using existing manufacturing contexts, I suppose, do it in a way that's reliable, etc. So we both are focusing on really working with existing expertise in manufacturing, so working with existing factories and manufacturing expertise, but integrating different sorts of fibers into that manufacturing stream to either knit or weave the sensors, the conductors, etc., directly into the textiles, into the garments, and that's what makes them reliable, scalable, and not cost prohibitive. And I'm very interested also in the next phase that we're already integrating into our manufacturing in terms of additive and also some amount of subtractive manufacturing. So adding to the knitting, to the weaving, through all kinds of ultrasonic welding, bonding, etc. And finally, as I mentioned earlier, I'm also working with scientists to develop the next generation of fibers that can, in fact, replace traditional electronic components. All of this, you know, basically to give this perspective on the Internet of Things, where our bodies, our human bodies, are, in fact, one of these things that will be connected. And in fact, as you mentioned, our heart rates are part of the Internet of Things. So this raises a lot of greater issues, greater than, you know, will somebody hack my car, but a lot of issues around privacy, et cetera, et cetera. So I look forward to discussing those.
Great, Joanna. Thank you so much. So I have one question for you before we move on. Let's just bookmark this and come back to it. But how many of the garments that you've engineered and experimented with have an IP address? You know, are they even connected to the internet, or are for the most part are they simply electronic rather than being sort of directly addressable on the network?
Well, they're connected through Bluetooth to another device that mediates their interaction with the network. So as to protect your privacy and so as to, well, do a whole bunch of other things. Both
Okay.
protect you and also streamline the data. Yeah.
Okay. All right. Let's come back to that in a minute. So thank you so much for that introduction. So next, let's go to David Harris at Harvey Mudd. David, can you tell us a little bit about what you're doing? You're more focused on the sort of the nuts and bolts of computer science. You're involved in VLSI design and other aspects of the basics of computing. So take it away. Tell us a little bit about what you're up to.
Great. Is the screen sharing?
Yep, we can see. If you can go full screen with that, that would be great.
All right. How's that look?
We're seeing the PowerPoint interface. If you can go into slideshow mode, that would be great.
I thought I did, but no?
No, we're just, I mean, it's readable, but we can continue this way, yeah.
Okay, we'll continue. So my interests on the Internet of Things come from two directions. One is from my background as a chip designer. I used to build processors at Intel and had a recent sabbatical at Broadcom. And I've been very interested in low energy circuit design. So, for instance, pushing voltages down to about half a volt to extend the energy efficiency. But today, I'm probably going to talk more about recent experience supervising some students using using chips to build devices to go on the Internet of Things. We have an engineering clinic program at Harvey Mudd College where our students take on projects sponsored by industry. We do about 25 of these a year for the last close to 50 years. And this past year we had a group of students develop a wearable medical device. So these slides will give a little bit of overview of that and our experience with the Internet of Things from this project. This was work sponsored by Excella Health. Dr. Stephen McCormick was the CEO and worked closely with the students. And I wanted to thank the students also for allowing me to share their work. So last slide first here. What I concluded from this, obviously Internet of Things devices have great potential, but we also discovered that the development process is still quite immature and painful. I expect that will improve over time. And then security, I believe, is going to be the major issue on the Internet of Things. So in this project, the doctor came with a mandate from the National Institute of Health to look at ways to reduce deaths from opioids. I think many of you know how addictive the opioids are and how easy it is for patients who need them while they're recovering from painful surgery to accidentally overdose. If the overdoses are detected early, there's medical intervention to save the patient's life. So the goal of this project was to develop a wearable medical device that could monitor vitals, collect information first for research purposes and eventually for summoning help to deal with the overdoses. So the student team developed a device that could monitor ECG, respiration, and motion. And then the sensors connected to a box that patient would wear that transmitted over Bluetooth Low Energy to an Android phone that in turn relayed the data onto the cloud for storage and analysis. So at the time, the Broadcom Wicked Smart Bluetooth Low Energy module looked like the most promising chip to run the system. But over the course of the project, we discovered that things like sampling an ECG at 140 hertz, which many of us would expect would be trivial for any sort of computing system, actually overtaxed the Wicked module. And students ended up finding the bottom-of-the-line PIC processor to end up doing data collection and some multiplexing and simplify the data so the load on the Wicked would get easier. The system runs at about a 10 milliamp power consumption, which gave it a one day battery life on a coin cell, or approaching 2 weeks on a lithium battery that could go in the box. And roughly half that power consumption was in the Wicked module and wireless, and half was in the sensors. So I'd say the largest challenge of the project was in just the immature and difficult embedded system development, doing anything on the bleeding edge. The documentation was poor. Anytime something went wrong, the visibility into the system was poor, and troubleshooting took a long time. The event-driven programming model was really unable to handle things much beyond DC. So the ECG sensor was a challenge and eventually had to be partly offloaded to the PIC. Similarly, doing timers and interrupts, any way to measure things at interesting data rates from the real world, overwhelmed the chip and had to be offloaded. And pinouts were really designed to handle perhaps a single function device rather than this number of sensors. Nevertheless, the students managed to pull off a project that worked. They hooked it up to the doctors, and doctors actually recorded data of their own vitals and saw it come onto the web, and everything looks really promising here. So as Internet of Things takes off, I think the primary challenge we're facing is that everything attached to the Internet has proven to be hackable. So government records, health insurance, major corporations, all that has suffered big data losses. The recent headlines about cars with Jeep Cherokee being able to hack its transmission and cut power to the car, force braking onto the Tesla. I think many of you saw the headlines of the tracking point rifle, where through the internet an attacker could take over the rifle. And then in Germany, the infrastructure attack, where the furnace in the steel mill was unable to shut down normally and caused serious damage to the factory. And then in bigger infrastructure, the likelihood of attacks on nuclear power plants and hydroelectric plants in the near future, I think, are really going to open up the government's eyes to the importance of security. So I've pondered what makes sense here, but overall I think attaching anything that's critical to safety of life to a wireless link is just asking for trouble. Attaching Internet of Things actuators to toys is great. My kids love the drones and being able to fly them from an iPad, and that's fun. But then at the intermediate level, what do we do about our homes, our doors? Should those go on the internet? Should a hacker be able to unlock our door? Should they be able to turn on our coffee maker? And so attaching Internet of Things to sensors seems like a safer bet, but anytime you have any attachment at all, there's always a risk of leakage. And so I remain concerned that as we attach all of these devices, we'll have viruses in the things that we're wearing, the things in our house, and we'll see some very interesting times.
No doubt. Thanks so much, David. So I want to come back to that Jeep Cherokee incident in a minute, but let's first go to Wendi Heinzelman at Rochester and give her some time to get us up to speed on what she's working on.
Great, thank you, Wade. So I was at MIT. I graduated, as Wade was saying, in 2000 with my PhD, and while I was there, I started working on what was at that point a relatively new field called wireless sensor networks. So there was a big study done by DARPA in, I think it was either the late 80s or early 90s, that was looking at kind of what was the next big use for embedded devices and communication systems, and they came up with this area of wireless sensor networks as having huge potential. And my advisor, Anantha Chandrakesan, who is still at MIT now, he's actually the chair of EECS, Core 6, he was part of that group that was looking at both the hardware and also some of the communication protocols for these embedded devices that have sensors on them. So for my PhD work, I developed protocols that allowed sensor devices, very, very low power sensor devices, to be able to hook up with each other, communicate without infrastructure, so in an ad hoc mode, and be able to transmit their data for long periods of time. So since then, I've been at the University of Rochester working on similar type topics, and I'm going to pull up my screen sharing here. Let me see if I can turn this on so you can see my slides. Oh, I think I... Okay, here we go. All right, is that showing up?
It is, Wendy.
Okay. And I'm trying full screen. We'll see if this works. So essentially, my work at Rochester in recent years has focused on trying to put some of these types of sensor systems in the home environment. And in the home environment, you want to think about things like wearable sensors. So all the things that have been discussed before in the clothing or on the body, you can gather sensor information about what the person's doing, the activities they're doing, physiological information. And then you might also have sensors throughout the home to monitor activity throughout the home and the environmental conditions throughout the home and things like that. We also are very interested in doing what I call sensing in the field. And these are putting sensors out somewhere in the environment to do a range of different applications. But these could be, as you see in this picture here, they could be everything from environmental sensors, sensing environmental pollutants in the air, temperature and humidity sensors for doing agriculture monitoring, water level sensors and water purification sensors, sensors on bridges and things like that. So the idea is we want to be able to gather information from the environment and be able to make sense of what's happening in the environment so that we can monitor and possibly affect what's happening. And so my research has focused on these areas in 4 different domains that I'm going to show you here. And one of them is this idea of something called a passive wake-up radio. The problem with wireless sensor nodes is that communication is extremely expensive. So Bluetooth, LTE, or low energy, if you use 3G communication, Wi-Fi is extremely energy hungry. And even if you use Zigbee, very low power communication systems, it still takes up a majority of the energy of your sensor device. So if your communication system's on all the time, waiting to transmit or waiting to receive, your battery is going to die and your sensor node won't last very long. So what we developed was something called a passive wake-up radio, where you have a device that is essentially an energy harvester, and it's waiting to receive a signal from a transmitter. And when it receives that signal from the transmitter, only then does it wake up the main radio for communication. So what this allows is the main radio for communication to be in the sleep mode for the majority of time of operation. You can save huge amounts of energy. In this project here, you can see a picture of the wake-up radio sensor node we developed. The application for this, we were working with faculty at Northeastern University as well as in 2 of the IITs in India to deploy these sensors in India to do pollution monitoring throughout the city of Hyderabad.
Wendy, we're actually, I'm sorry, this is Wade. We're only seeing the first slide. Have you advanced to the next slide?
Oh, I have, yes. Should
okay. That might be a Google Hangouts problem, and I might be wrong.
Is it there now?
Yes. Now we're seeing slide 4 of 4.
Okay, let me Okay, can you see it now?
That's 2 of 4.
Oh. All right, then
and
let
again,
me just
I'm not sure everyone's seeing the same thing here.
Okay, I'll keep it like this. If you can see this, I'll keep it in.
That's great. Thank you.
So, so we developed these passive wake-up radios to do environment monitoring in India, and the idea is that you can put these devices throughout the city, and they're measuring certain pollutants in the environment, and then every so often, maybe once a week, maybe once a month, depending on different conditions, a car will drive by that has a wake-up transmitter that will be emitting an RF signal that essentially pings the sensor node and wakes it up. And at that point, the sensor node wakes up, turns on its communication, its radio, and can communicate the data back to this sync that's driving around collecting the data. So in this way, these sensors basically are only sensing data periodically, and the radio is off until the sync comes around and can collect data. So this fits in very nicely with that Internet of Things, with the idea of trying to make these devices last for as long as possible by ensuring that their components are not used unless actually needed. Another aspect of the Internet of Things and sensor networks that we've been working on is shown in the lower part of the slide over here, the lower left side, where we're looking at energy harvesting. Because even as low as we make the energy, eventually if you're running on batteries, the batteries are going to run out. You either need to change them or the system's dead. So an alternative is to use energy harvesting, and you can harvest energy from RF waves, ambient RF, you can have directed RF, you can have vibration energy, solar energy, and these are things that can allow you to power your devices. And this is going to be really important as we move forward for creating these devices, especially field systems, the devices we want to put out in the environment and we want to last for very long times. So we've been developing some approaches to say when you have systems that you want to reduce the energy as much as possible, but you also know that energy might be replenished at certain points. How does that change how you operate your systems and how you run your protocols? And we have a project looking at that. Sort of on a different side of things, we've also been looking at how you can do computing and distributed computing in an environment where you have processors all over the place. So if you think about your cell phones, these things are actually huge processors. They have about the same capability as laptops of just a few years ago in terms of their computing capability, their memory storage, and so forth. And for the majority of the time, your cell phones are sitting idle, especially when you're sleeping. And we've developed a project where we created a volunteer network where we can utilize the spare cycles on cell phones to do computing for very large computing projects. And we were working with a company, a drug discovery company, that has a lot of computational needs for understanding protein structures and things of that nature. And they basically don't care. There's no timing constraints for when it gets done. They just have lots of computation that needs to get done. So we just developed an architecture that allows any cell phones that volunteer their free space, we can run that computation on the cell phones and send back the results. And we've extended that so that the cell phone doesn't even have to be on the network. It doesn't have to be Wi-Fi connected or connected through LTE or 3G. It can be connected through a new standard called Wi-Fi Direct with point-to-point communication with another device. So as long as you're connected with some device, you can actually take part and participate in this distributed computing environment. And then the final project that we're working on is actually a little bit different from all of these that focus more on communications and networking, and that's trying to do automatic classification of emotions from speech. And the idea here is we're going to have lots of these sensors, including microphones that are available, particularly in the home. Can we use the information that we're gathering from these sensors, from these microphones, not to listen into conversations to try and detect if people are mad or happy or excited, but use features of the voice, and from that try and detect what the emotions are of the participants. And this has lots of applications in the medical space as well as in psychology and studying human interactions and behavior and gaming and things of that nature. So that's a brief summary of what we've been working on for the last few years related to the Internet of Things.
Super. Thank you so much, Wendi. So each of you, it strikes me, is pushing forward on the against the boundaries of internet-connected devices and materials as hard as you can. And while none of you is necessarily a security researcher, I think that the one question that you're going to get, probably the first question you would get in any public forum where the Internet of Things is on the table is what about security? And David brought this up in a very poignant way. He mentioned the the Jeep Cherokee and some other sort of interesting hacking episodes. I think that the Jeep Cherokee thing, which was only a couple of weeks ago, where a Wired reporter had was working with a duo of hackers who basically hacked in to his Jeep wirelessly from about 10 miles away and managed to mess around with the entertainment system, and through that get access to the transmission and other vital functions, and in a sort of perhaps over-dramatized moment, cut the transmission right as a semi-trailer was bearing down on the Jeep. or so we're told. Okay, what I want to ask you is, was that a stunt, or do you think it was actually a kind of a useful lens by which we can kind of help to focus concern and attention on a very important question, which is, as we build internet connectivity into more devices and machines, have we really figured out how to stop bad actors from taking advantage of that in ways that we don't intend? So, David, I'll let you speak to that first, since you mentioned the Jeep incident in your presentation.
Right, and that just led to a recall of what, 1.4 million vehicles a couple weeks ago. So, we obviously haven't solved the hacking problem in PCs, where it's the easiest problem to solve because we really only have to solve it on a handful of operating systems. With Internet of Things, we have a vast number of devices running vast number of different pieces of software, all developed, many on a low budget by less experienced organizations. I don't think there's any hope of solving the security problem there except by avoidance. I believe anything that goes on the internet will be hackable.
Yeah, you said that it was just asking for trouble to connect life, systems where there's a life in the balance to the internet. And do you really mean that? I mean, I'm going to show my science fiction bona fides here and make a Battlestar Galactica reference. In the first step, it was made clear that Commander Adama refused to have sort of internet-connected computers on his starship because he was afraid the Cylons would hack into it, and he was people made fun of him for that. But in the end, it's exactly what saved the Battlestar, right? When the Cylons attacked. So, which sounds great in theory, but in practice, we actually need to push forward and find more efficient ways to manage traffic and to keep people safer, right? And connecting cars to the internet might well be one way to do that. So we can't really just stop progress, right? So is it realistic to not connect things to the internet?
I think we are going to go ahead and connect things to the internet, and then I think we're going to regret it.
So Joanna or Wendi, how can we reduce the chances that we'll regret it?
So, I'll let Joanna go.
Oh, I just wanted to push your reference a little bit further, right? So the spaceship wasn't hacked through wireless communications, but was hacked by programming people, in a sense, right? So, just as hacking things that are connected might seem inevitable, something will always get hacked, right? And then do we stop? No, we certainly don't. We do keep pushing, as you said. But anyway, that's not an answer. I just wanted to to add to your reference.
No, good point. We'll take it. Wendi?
Yeah, I wanted to echo that. I think that certainly anything that is connected is going to be hacked in some way. Even things that aren't connected can still be hacked. It's certainly harder because you have to be more physically present. But credit cards get hacked when you've got the devices right there. People can overhear you saying your credit card number. There's lots of ways things can get hacked and stolen. And so I think what is important is to keep in mind that especially with mission critical data, and as David was saying, when you have health critical or life critical information, that has to be at the forefront, is to protect as best you can. But I agree completely with Joanna that you can't just stop trying to move forward with this, because the benefits are going to far outweigh the risks in a lot of cases.
Right. Just today or yesterday, there was an interesting op-ed in the New York Times basically saying that, let me see if I can find it here. The headline was, "Why Smart Objects May Be a Dumb Idea," and it mentioned the Jeep incident and a whole bunch of others, and basically the argument was that with systems like cars where the operating system, the underlying operating system was not built in a secure way, it may just not be possible to connect those things safely to the internet unless you rebuild the infrastructure, right? Mm-hmm. So that a car needs an inherently secure operating system before you connect it to the internet. That was the argument anyway. Does that seem even remotely plausible, or would that seems to me like it would require a sort of a five-year timeout to just get to that point? David, from your experience with medical devices, I mean, can you imagine making a medical manufacturer kind of rebuild the firmware on their devices before anyone was allowed to hack around on them the way you were with the drug machine?
Well, I think it's a noble undertaking to try to build an OS for IoT that is secure. And if somebody succeeded at it, I think they'd have a huge market. I'm not optimistic, given the record of the computer industry, that we will succeed at such a thing. You talk about the benefits outweighing the risks. But let's take a nuclear power plant, and say hooking it to the internet allows us to gain some efficiencies in energy, 20 or even say 30% better utilization of the power. And the risk is that either a state actor or a non-state actor could cause the power plant to melt down. Is that worth the risk? Is it better to have people walking back and forth to the controls and actually pushing the knob to adjust the rods? It seems to me that I'd rather be paying the person to push the rods.
Although Stuxnet showed that you don't even have to be on the internet in order to destroy someone's infrastructure, right?
And that brings to a good point. You obviously don't have to be on the internet, but when you are on the internet, you become vulnerable to automated mass production attacks. While when you're off the net, they have to be handcrafted and take a fair amount of human labor to attack. Right,
okay. We have a whole bunch of questions piling up from viewers, and so I'd like to go to some of those questions now. So here's one from Toby in Newton, Massachusetts. He asks, what are the implications for using the Internet of Things in crime or police work that worry you or excite you? So, I mean, I'm not sure what he has in mind specifically, but one can imagine things like, well, systems of sensors out in the field, maybe low power sensors that are out there providing some kind of surveillance capability. So, Wendi, have you had people asking you whether your technology could be used for surveillance or law enforcement?
No, I haven't addressed that in the past, but I know in London, for example, they have cameras all over the place that are connected and that they do use for going back and trying to figure out what happened in certain places. I mean, even in Boston, right after the attack at the Boston Marathon, there were lots of sensors, and not just cameras that were in the streets, but people's cell phones. Right now we have crowdsourcing, and people are gathering data through their phones, through the cameras, through the microphones, through other sensors on the phones, that we can then go back and actually use to help solve some of these cases. And I believe in the Boston Marathon case, that was one of the big things that led them to find the attackers in that case. So I think that there's great potential in utilizing the sensors that are available to help in these types of cases. And another one I've also seen is when kids go missing. So they have the Amber Alerts that go out, and to be able to send information from people's cell phones about crowded places, they can use that to try and locate kids who have gone missing. I think there's a lot of great opportunities to be able to help in solving some crimes using these sensors.
Great. I want to keep us moving along. We have a question for Joanna that came in from Brad in the United Kingdom. Joanna, Brad is asking, dare I ask whether there's any commercial prospect with wearable fashions for the masses? Is this something we'll see only on the runway, or could it be in Walmart 5 years from now?
So I'm actually a big believer in material science, right? So that a lot of the approaches right now to smart garments have been driven by the consumer electronics way of thinking, which is about defining what is the function of this garment. And that's why a lot of them, including our Signal product, focus on things like fitness, the quantified self, health, etc. So things that can be quantified, where some kind of productive, useful outcome can be quantified. Fashion, on the other hand, functions in a completely different modality, right? Where it's not about quantifying results. It's actually very often about the irrational, about playful, about feeling good, or even about wearing something that's provocative and not necessarily efficient, right? And that's certainly what we see on the runways, but that's how I actually see a lot of these material technologies, a lot of the kind of stupid kinds of applications, like just having a little blinky light that shows that somebody clicked your picture on Facebook, you know, things that can connect us in silly, irrational ways. Just like the kids' sneakers that were blinking when they would run, right? I think you can still buy those. So I actually see a lot of potential for those kinds of products. And as I mentioned in my little presentation, the biggest stumbling block is manufacturing, and that is something that's really changing right now. So these ideas have been around for a long, long time. The manufacturing was the barrier to entry. And all the huge manufacturers are realizing that they really need to tackle the problem of integrating new materials and electronic materials in traditional manufacturing streams that isn't only a manufacturing stream of industrial design, but also garments, if they want to survive. So I definitely, yeah.
Great, great. So on the materials question, we have a related question coming in from Fred in Painted Post, New York. He asks, is it possible or desirable to use optical fiber in textile manufacturing?
Yeah, optical fibers have been used as sensors to sense the deformation of cloth, or also discontinuities in cloth or triage in the field. So yeah, the problem with optical fibers is that the ones that are really good at transmitting light are also very brittle. So I'm actually working with a collaborator, also an MIT alum, Maxime Skrobogati, to develop different kinds of optical fibers that are much more pliable, that can be woven without breaking, because there is a lot of potential there, both for transmitting, but also as for the sensing capabilities.
Right, okay. So returning to the security question, we have a question coming in from Michael in Massachusetts who asks, how do you get a security update onto one of these internet-connected devices as a weakness is discovered? It's difficult to recall some of these devices. I mean, it's hard enough to recall a Jeep. Can you recall a dress? Can you recall a watch? So, David, anyone else? How do you get new software onto these devices without having like a field agent go there with a USB stick?
Well, the safest way is the USB stick, and that works for the high-ticket items. Anything where the device is reprogrammable over the internet, again, creates opportunities for even worse hacking. And I think we will see lots of those devices deploy. We're already seeing, for instance, the reprogrammable gun, where the attacker can rewrite the firmware in that weapon remotely. So yeah. I think that updates are extremely dangerous.
Wendi, I bet you have a slightly different point of view, because the ability to change the software is sort of one premise of the usefulness of having a network of ad hoc connected sensors, right?
Right, and I mean, there's been a lot of work done on how to do that and how to make sure it's robust and security. I agree with David, though. That is a huge issue. When you can update, it's a backdoor way into just changing the devices to use them how you want to use them, or to shut them down so that you can't get access to them. So there is a big security issue there, but I think when you've got hundreds of devices, it's critical to be able to access them in the field. Again, it's that risk-reward trade-off, and you have to decide, if these are sensors that are monitoring the pollution in my environment and someone hacks into them and then suddenly I can't get any data out of them, it's not loss of life and limb. It's loss of data, which is annoying, but that it's the right trade-off. Would I do the same thing in my sensor that's monitoring my heart rate? Probably not.
Okay. We have a question coming in from Ellen in Cambridge about privacy, sort of, and how long information collected via Internet of Things devices will be kept around and who gets to access it. So what's your best guess about who would have access to personal data collected by remote devices, internet-connected devices, 5 years from now or 10 years from now, would that information have to be erased at some point? Are there any laws and regulations around this? Have you guys thought about how long you're going to keep your data?
So if I can just jump in, one thing that David mentioned earlier is that a lot of the teams developing, these devices tend to be startup companies, teams that perhaps aren't as experienced or that are operating under certain conditions where they have to develop quickly without necessarily kind of robustness, right? Another aspect of that is that developing these devices might go out of business within a few years. And then, this question of who owns that information becomes even more problematic, right? Because they might have the best intentions and have some kind of like double level of security and having things be completely anonymous. But when the company goes out of business, who controls what happens to that data? And especially the very sort of personal medical data collected on our bodies.
Okay, well, we are at the 45-minute mark. I would like to do a quick lightning round. So you each get basically 20 or 30 seconds to say whether you are more excited or more fearful about the Internet of Things, and if so, why. But really just 20 or 30 seconds, and then I'll take you out and we'll say goodbye. So let's go in alphabet order again. Joanna, so are you more excited or more fearful?
I'm excited if we leave out, the nuclear plant scenarios, right? So, but I'm more excited because also our definitions of privacy, our definitions of security are changing all the time. Our levels of comfort are changing all the time. So I think there's a lot of interesting developments that we'll see in our lifetimes.
Thank you. David?
I'm excited, but again, I would hope that our society develops the wisdom to keep the safety of life devices off of this Internet of Things.
Okay. And Wendi, you get the last word.
I think that there's great potential in everything from healthcare to sustainability, the environment, improving agriculture. There's just so much potential in this field. I think we have to go in with our eyes wide open, but I think there's just so much potential that it's a very exciting time.
Well, I agree with you, but also an interesting time. There's going to be plenty of fodder for journalists like me. So, okay, well, I would like to, on behalf of the MIT Alumni Association and the Knight Science Journalism Program, I'd like to thank each of our MIT alumni panelists from Harvey Mudd College, Concordia University, and the University of Rochester. I'd like to thank our audience also for tuning into this Faculty Forum Online Alumni Edition. We didn't get to all of the questions, but we will pass on the remaining questions to our panelists after the session. And you can keep tweeting about the event at the hashtag MIT Alum, or send us follow-up questions or feedback at the email address alumnilearn, that's all one word, alumnilearn@mit.edu. Thanks again for watching, and this is Wade Roush signing off from beautiful Durham, North Carolina. Thanks so much.
Thanks again for joining us. For more information on future MIT Alumni Association productions, please visit our website.